general relativity, step by step. I've developed this nice energy equation here, dr by d tau squared equals this expression here, dr by d tau squared equals k squared minus 1 over r. And here I'm using units in which 2 gm over c squared equals 1. So my Schwarzschild, easy to spell wrong, child radius equals 1. So that's my length unit. And my time unit is defined, so the speed of light is equal to 1. If we consider k equals 1, this is the simplest case. This is sort of a parabolic case. Because the limit as r approaches infinity of dr by d tau squared, the limit as r approaches infinity of that, equals k squared minus 1 equals 0 if k equals 1. So that says that far away from the black hole we've got 0 kinetic energy left over. So it's a limiting case, it's a parabolic case, corresponds to 0 kinetic energy at infinity. And the mathematics is much, much easier, as we'll see. So what have we got? We've got dr by d tau squared equals, from here, 1 over r. So that says that dr by d tau equals plus or minus the square root of 1 over r. And of course the plus or minus depends upon whether we are considering an inward trajectory or an outward trajectory. So that tells me that d tau equals plus or minus dr times r to the 1/2. And of course we can integrate that from, so delta tau equals the integral from r equals r1, let's say, to r equals r2. We're moving from radius 1 to 2 along this line specified, this geodesic line specified by k equals 1, of r to the 1/2 dr, and of course that's easy. That's 2/3 r to the power 3 over 2 from r equals r1 to r equals r2. I guess we've got, yeah, we normally consider dropping, so we consider dropping from a large radius to a small radius. And if that's the case, then of course we need the negative sign here because your radius is decreasing with proper time. Delta tau equals this. So we can drop from r equals 3 to r equals 2. And what have we got? We've got that the time required for that, the proper time, the wristwatch time, equals minus 2/3 r to the 3 over 2 from 2 to 3. No, we're dropping from 3 to 2. That's it. Yeah, that's it. So it's 2/3 3 to the power 3 over 2 minus 2/3 2 to the power 3 over 2, which is a nice value which I could calculate if I wanted. The interesting bit comes when you start to say to drop from, let's say, r equals r0 to r equals 1. And of course the answer to that is we just go through the same mechanism, and it's again 2/3 r0 to the power 3 over 2 minus 2/3 1, not sure what happened there, 1 to the power 3 over 2, finite again. I can factorise it a little bit if I want. 2/3 r0 to the 3 over 2 minus 1. Finite, very finite. For any value of r0, that's finite. It takes a finite amount of time to reach the event horizon, which is in stark contrast to the picture of the Schwarzschild geometry, which I've been talking about here, in which even ingoing light rays take an infinite amount of Schwarzschild time to reach the event horizon, to reach r equals 1. What we're considering here, what we're looking at here, is a discrepancy or a difference between Schwarzschild time and proper time. And of course that difference gets magnified, that difference gets bigger and bigger and bigger as you approach the Schwarzschild radius. No, I didn't mean that one, I meant this one. Try again. There we go, so that's finite, which is quite interesting. We can also drop from r equals, let's say, 1 from the Schwarzschild radius, to r equals 0, and that's the singularity in the centre of the black hole, and by the same token the proper time, delta tau, equals 2/3 1 to the power 3 over 2 minus 0 to the 3 over 2 equals 2/3. Finite again. The problem is caused by the fact that this vertical axis is Schwarzschild time, which is a poor choice of coordinate to describe or to even think about what happens to proper time, because you've got this asymptotic behaviour here. I've got another diagram here, which I've scribbled on already, but I can get rid of that. And this is the same as before. It's exactly the same diagram. Everything's the same. I'll get rid of my annotations. It's exactly the same, except I've drawn these dotted lines here, and these dotted lines show ingoing geodesics corresponding to the case k equals 1, that show that the infalling objects also have this asymptotic behaviour here. Well, they're constrained. They can't go steeper than, well, they can't, I was going to say they can't go steeper than 45 degrees, but they can't go steeper locally than either the ingoing red or the outgoing blue null geodesics. You're constrained to be within your light cone here. And the same occurs inside. And we've got this, again, similar behaviour when we are going backwards in Schwarzschild time, because Schwarzschild time is a poor coordinate for thinking about what happens inside the Schwarzschild radius. Yeah, I think this is hard work. There's quite a lot going on here. I'm going to spend quite a long time talking about different coordinate choices for describing the geometry near a black hole. I'm going to stop there. Stop.